My name is Helmut Rechberger. I'm from Vienna University of Technology. I'm a professor for resource management, and we are doing research on developing methods to analyze, to evaluate, and to design the material metabolism of industrial societies. What we have seen in the past, and I'm sure it's certainly not new to you, we have increasing demand and supply of resources. Some resources have increases linear or even exponentially. As you can see, for example, aluminum, please be careful, there are different y-axes. Aluminum or cement, these are construction materials where we saw really dramatic increases in consumption. We also have a few other materials where we see more or less stagnation. For example, here the red line is for lead. So the world consumption of lead did not really increase over the past decades. Why? Yeah, one of the reasons was that we found out that lead is hazardous, is a hazardous material, so we don't use it longer for water pipes, for example, and things like this. Or in leaded gasoline or so, we still use it for car batteries, and this is more or less the main application of lead in our days, and there the recycling works also quite well, at least in the developed countries. So we also see materials where we have more or less a stable state or stagnation of consumption, but I would say for 80–90% of the materials which we use, we see increases. And the German Bundesanstalt für Geowissenschaften und Rohstoffe, they once calculated how much materials are consumed over the lifetime of an average German person. And here you can see altogether, this is around 1,000 tons that are consumed over the lifetime. And this is quite an amount, 1,000 tons. This is, for example, 3 times the weight of an aircraft, of a large aircraft, of a A380, for example, or it's the weight of around 670 cars. So these are really large materials, amounts of materials that we consume. And if you have a closer look to these materials, you see, for example, from a point of view of mass, the most important materials are sand and gravel, but also hard rock, limestone, for example, steel. These are all construction materials mainly. They are used to construct buildings and the infrastructure. So most of our, in terms of mass, most of our materials go into the construction sector. A second phenomenon that we see is that the urban way of life becomes dominant. We have seen this, of course, in our developed regions. We know that around up to 80% of people are already living in cities. We have growing cities, many more so-called mega cities that have more than 50 million of inhabitants, but also in other regions, they are quickly adopting to our urban way of life. And the United Nations think that around the year 230, that between 60 and 80% of world's population will live in cities. For me, as a resource manager, this is quite a good, a good outlook, because this is quite, it sounds like this is a concentration, and if materials or whatever is, if it's concentrated, then it's much easier to be controlled. The other way would be if everything is dispersed or diluted or so, then it's difficult to control something. So concentration per se, for me, is not a bad issue, so I think that's quite a good development. If we want to calculate the weight of a city, we once did it for the city of Vienna, then the metabolism of a city is dominated by its water consumption. So these are numbers in tons per capita and year. So each Viennese person consumes around 150 tons of water per year. And all this water is discharged to the river Danube via the sewage. It's purified water, wastewater. This is the water that the citizens of Vienna use, but also the industry and so on, and commercial enterprises and so on. Then the next important flow of material is air, but this is not only the air that we have to use for breathing, it's also the air that we use for combustion processes, and it's the larger amount. And most of this air, also some things are evaporated, and also the energy carriers, they leave the city via the exhaust or the off gas. But then we see we consume around 12 to 18 tons of solid materials per capita and year. And most of these materials are construction materials, around 10 to 15 tons. At the output side, of course, we have some industry still in Vienna, so we still produce a few products. Then we produce the so-called household waste that everybody of us is aware of. This is everything what we throw into the dustbin. It's also the separately collected waste, but we produce another type of waste which seems to be an order of magnitude more. And much of this waste is, I would say 1/3 is industrial waste, but 2 tons approximately is again construction and demolition waste. And as you can see, the input of solid materials is quite large compared to the output of solid materials, so we have a net stock increase. So around 10 tons per year in capita is added to the already existing stock that we have estimated to around 400 tons for each Viennese person. Again, you can imagine 400 tons, quite a big amount. And 10 tons are added each year, so in 40 years, Vienna would be twice as heavy as it's today. If it's just if just the current situation is extended. This is not a good message, at least for our understanding, because I mean, in 40 years, maybe we have 2 million of inhabitants here. Now we have 1.7. But if we have twice as much as material, this means that we have to maintain all these buildings, all this infrastructure that we build up. And you know, maintenance means you have to have the money to keep all the things running. So somehow we are a little bit concerned about these large growth rates that we see in many cities, not only in Vienna. These 400 tons per capita, we don't have really good information which materials are in these 400 tons. There's been one study for Switzerland, and I think these numbers are also quite applicable for Vienna. Of course, the large amount of this stock consists of sand and gravel, bricks, but then we already see that 5 to 10 tons of steel are contained in our buildings, in our infrastructure, per capita. So each of you possesses around 5 to 10 tons of steel. This is not the car, the passenger car. Most of this steel is construction steel in buildings or technical steel in infrastructure. Then we see, for example, 1 ton of plastic is contained in this stock. This is plastics for floors and so on. I don't know if you have an idea how many plastics you are separately collecting per year. So the PET bottles and the small plastic bags and so on that you collect. The numbers for Austria are around 15 kilograms per year in capita. So this is what we collect each year, but we have 1 ton in the stock. So you see this is a quite considerable amount. 300 kilograms of copper per capita. This is the global cycle of copper, as has been calculated or determined by Tom Cradle at Yale. And I just want to draw your attention to these two red numbers. This is the copper. These are just pure numbers for copper. This is the copper that is contained in the reserves. So these are the copper ore bodies that are economically extractable and which are exactly identified. So we think that around 580 million tons, so that the unit is here kilotons, 580 million tons of copper are still contained in copper reserves, and we have estimated that the copper that is globally in use is around 300 million tons. So you see at least these two red numbers are in the same order of magnitude. Okay, these 300 million tons here, they are used by, let's say, the rich people, so by us. And you have seen for Switzerland, the calculation was that each Swiss person possesses around 300 kilograms. I would say for Vienna we did, or for Austria we did such a calculation. We think we have around 250 kilograms. I would say people in the high developed countries possess around 200 kilograms of copper. If you take this number here, the 580 millions, and divide it by 7 billion of people on the earth, you see that for each citizen, there would be around 80 kilograms of copper still in the soil. So just to give you an idea, 80 kilograms that is still here reserved for each of us, and we already possess between 200 or 300 kilograms. So we say in future we should try to maintain our living, our way of living with this amount of copper, and we should try to use as less as possible from these primary copper reserves. They are more, I would say, they are more reserved for the people who don't have any copper today. So this is one of the reasons why we think, and we say this is primary copper, and we designate this type of copper as anthropogenic copper. So it's already copper. This is copper that is already has gone through our hands and has been processed by people and so on. And we say these are the types of resources that we should use in future and try to recycle them as good as possible. So what we are doing, we are developing flow charts of resources for developed industrial economies. Mainly we do this research for Austria, and here you would see the aluminum cycle for Austria for the year 2010. So this would be a typical flow chart where you see that most of the aluminum is imported to Austria. We can then see which different types of aluminum are produced, in which different applications this aluminum is then transferred or transformed. Here at the back end we see in which types of ways we can expect aluminum flows, and we can also see how large is the recycling stream back into the production process. And this is the first step that we use to analyze the situation, to understand what is going on, in this case with respect to aluminum. But we don't do this for 1 year, we do this for several years, and we produce dynamic models, so models that change over the time. And one of the results of such a model would then be that we can estimate the build-up of the anthropogenic stock of, in this case, of aluminum. So what you would see here is that the total stock of aluminum in Austria in 2010 or so is approximately 3 million tons of aluminum, and this aluminum is contained in the transport sector, so this is mainly cars, and it's contained, the largest part is contained in buildings. So this is where we have to look for aluminum in future. And this would be, so the total stock of aluminum has been estimated to around 300 kilograms per capita in Austria. And this would be the aluminum scrap that goes or it becomes available in the waste management system. And there we would see most of the aluminum that we can get, aluminum scrap that we get today is contained in cars. But unfortunately, 2/3 of the cars are just exported to other regions, to Africa or to Eastern regions. So it's lost for our industry, for our economy. And the largest part of aluminum we find in packaging materials, in aluminum cans, in aluminum foils. Sometimes they are very difficult to recycle because these are very thin wall applications and it's difficult to recycle them. And the current production of aluminum scrap is around 12 kilograms per capita and year. If we have such a model, then we can also make extrapolations into the future, and we try to make estimates how will this continue in the future, and make estimates in which types of wastes we can expect the highest amount of aluminum scrap in the future. Because if you see the build-up of the stock, and all these materials have different residence times in the stock, then we can estimate that the partitioning between the different applications here will be quite different in 5, 10, 15 years. But I will come back to this point later on. A second and completely other approach that we apply is now very focused on the building sector. We try to investigate buildings that will be demolished in the future. This is a project that we do together with the city of Vienna. So we select different case studies, which means these are different buildings that are going to be deconstructed or demolished in the next time. And then we have the opportunity to go into these buildings, make inspections and take samples. And what we try to do is we try to determine the material composition of these buildings. So we try to find out how much concrete, how much bricks, how much steel, and so on is contained in this single building. And we do this, as I said, by inspection, but also by reading construction files and, let's say, by getting all kind of information that is available about such a building. And with these investigations, we try to analyze the total building structure of Vienna. We merge our data that we produce with GIS data. And finally, we would like to make estimates about the quantity and the quality of construction and demolition waste for Vienna, in this case, in the next years. And how we do that, I will show you in the coming slides. So this would be typical case studies that we have selected. So you see these are really large buildings. So this is, for example, a very large residential building. These buildings are different types, from different have different construction years, and my people, they go into these buildings, and sometimes they really take samples. For example, they determine the number of windows, they determine is this a wooden window or is it from plastics or from aluminum, and so on. They weigh the heating systems, the networks, and so on. And this here would be one typical example for such a building. This is a residential building, a so-called Gründerzeithaus, which means this is a building, one of these beautiful buildings that you can see in Vienna, which have been built around 1900. So the age is around 100 years or so. And these buildings are made up of bricks mainly, but also they have large amounts of concrete, sometimes in the basement as a stabilization, later on, or also the floors sometimes are made of concrete, you would find, for example, 500 tons of steel in such a Gründerzeit building. For example, around 10 tons of aluminum and copper, significant amounts of plastics or PVC. And what we also determine, not only the total amounts of these materials, but we know where is the PVC, for example, contained. So most, or let's say 50% of the PVC is in floors, like here. The other 40% are, for example, the coating of cables, and a few other tubing, for example, where PVC pipes are often applied. This would be one result of one of these case studies, but what we want to do is we want to produce such specific numbers, specific material compositions in kilogram per cubic meter of gross volume for typical buildings. So here you would see the result of 6 case studies. Currently we have already up to 20 case studies, and we will have a few more in the future. And what you can see, for example, is it seems that in such a building the amount of steel is between, let's say, 5 to 7 kilograms of steel per cubic meter of gross volume of the building. But then you can see, here it's completely different. This is a building constructed in 1890, like this building. Why is the steel content so low here? I can assume that the content of wood would be rather high for this building, and this is true. Then I know, okay, the floors of this building are still old floors which have wooden construction beams, and in this building, for example, these beams have been substituted later on by steel beams. But somehow you can imagine that it should be possible to get typical material intensity data for typical buildings, and this is the goal of these investigations. We try to get these numbers not only from our case studies, where I have said maybe we have 20 of these case studies in the future. We also get construction files from buildings that are going to be demolished in Vienna, from the city of Vienna. We got around 200 of these construction files, and we also use these construction files to determine the material composition of these buildings. So we have a lot of more data or information that goes into these tables. But what we then want to do is, if we have such a table, we merge this specific material data with GIS data, which is where we have a really good database in Vienna. The city of Vienna has GIS data for each single building. So we know the height and the area of the building, so we can calculate the volume of each single building. And we have also data about the year of construction of each building, and about the usage of these buildings. Is it a residential building? Is it a more commercial building? So we know quite a lot about each of these buildings, and if we merge these information with our information, which our specific material information, then it should be possible to determine the material composition of a single building. So then we can go through Vienna and look at the building, and I can tell you, okay, in this building we have 5 tons of steel and 3 tons of aluminum, and so on and so on. Of course, we will have quite large uncertainty ranges. But if we add up this for hundreds of buildings, then the uncertainties will be leveled out and will be reduced. And finally, we would like to have this to make predictions for two different addresses. The first one is again the city of Vienna. They would like to know how much construction and demolition waste will be generated in the coming years, and what will be the composition of these wastes. How much aluminum scrap, how much steel, how much copper can they expect? And this is also important for the local recycling industry. They want to know how much scrap can they expect in the future, because the amounts will be quite different from the amounts that we see today. And on a larger level, also the industry is very interested in such kind of materials, of information. Again, the aluminum industry in Europe, they really would like to know how much aluminum scrap can they expect in 5, in 10, in 15 years. Because they know what they have sold over the past 20 or 30 years. They know they have sold a lot of aluminum, and they would like to know, when can we get back this aluminum? Because they have to know, do we need the additional smelters, for example? Or do we have to close down smelters? And if you need an additional smelter, you cannot just turn off a smelter. Like this takes years to erect or to plan a new smelter. Means you have to have 5 or 10 years. So they have to plan into the future, and they would like to know which quantities can they expect in the future. And this is what we want or try to deliver for these types of industries. So how far have we come? I think we have now quite good methods to determine the anthropogenic stock. We have demonstrated that the method is available. It's just an issue of how many case studies you are willing to investigate. I mean, we did it now for 20, but we could do it also for 50 or so. It's just a measure of, or a question of how much labor you want to invest in it, but it's possible to determine this stock. Of course, we have to classify this stock into reserves and into resources, which means all the aluminum that is contained in Vienna is not a reserve, which would mean that it can be economically extracted. Some of this aluminum you never will get because it's too expensive to get it out from the soil or so, for example, or copper. So part of this stock is, of course, resources that are more or less lost for ever, or for long times at least. And what we would then do based on our knowledge is to make sound predictions about the waste generation, about the generation of scrap in the future. These are then the secondary resources for our industries to produce secondary materials. And our vision that we have is that such a city somehow recycles itself at a very high recycling rate. You know, 100% is of course never possible, but maybe at the recycling rate of 80%, so that the materials can be used again and again, and only the small amounts that cannot be recycled should then come from primary resources. And by such a scheme, we could reduce our dependency on imports of resources dramatically, especially in Europe, where we don't have much primary resources. This would be our vision, and I think we are on a good way to have all the methods and the information so that we could establish such a scheme over the next 10 or 20 years. Yeah. So far, our vision. Thank you very much for your attention.